lecture series. I'd like to thank the late Russ Frank, who was our donor for 14 or so years, and now our new donor, Daniel Schuman, and also our dean, who guided us over in the sort of transition period and made a sort of smooth transition to keep going with this. I'll keep it short. One thing I want to let you know is we have an email list. So if you got an email about this lecture, then you're obviously on the list. But if you didn't and you'd like to, then at the end of the lecture, you can just leave us your name and email, and I'll put you on the list for future lectures. I should say my name is George Shri, I'm a professor here in the Department of Physics and Astronomy. And it's a great pleasure to introduce one of the most distinguished astronomers / scientists in the world, Shri Kulkarni. We're so honored that he could take time off and come here and do this public lecture. I won't read his whole CV, so I think it's better to listen to him telling you stuff than me reading out about how distinguished he is. But he's a George Ellery Hill Professor of Astronomy at the California Institute of Technology. He got his undergrad degree at the Indian Institute of Technology in Delhi, and his PhD from UC Berkeley. He's won all sorts of honors. He's a fellow of the Royal Society, the oldest scientific society in the world, member of the National Academy of Sciences. I could go on, but I will highlight his most recent honor, which is he was awarded the Shaw Prize in Astronomy in 2024, which is just one step away from the Nobel, or equal to the Nobel, I would say. And the guy who chaired the committee was one of our previous speakers that awarded the prize, so you're really in good hands here with this lecture series. We're bringing you the best scientists in the world here to UNLV. And he's going to talk to us about the restless universe, how the periodic table got built up. So welcome, Shri, and thanks again.
Well, this is a good lecture hall because I have a prop already built in here. This is the periodic table. And we'll try to understand how we got all these elements. The universe didn't begin with these elements. Okay, that's a story I'll tell you. This will be a slightly different sort of a public talk than probably you heard, because it'll have elements of first of all, I'll give you my view of science, which may be somewhat, I would say, not so common. And I'll also tell you a little bit about how science actually gets done, because many people, and I hope there's some young people, and even old people will think that, oh, the scientists are there in their ivory tower and breathing very rarefied air or something. But it turns out the point I want to make is very simple. Science activity is like any other activity. Okay, and I'll show you the sort of style of science I've been doing is more related to being an entrepreneur. Okay, and when an entrepreneur, you have an idea and you want to make money. And as a scientist, you have an idea and you want to write papers. It's just a different currency, okay? But it's all otherwise the same thing. You have an idea, you have to sell it to other people. You have to get venture capital, i.e. grants, or convince the dean maybe in the beginning, and then make it big. And then if it's all worked out well, then you have to convince other people to join your enterprise, especially young people, because they have a lot of time and energy. So it's the same thing. So I want to demystify the idea that scientists sort of do like little weird people doing things that are out of this world. We are studying things out of the world, but we are very much in this world. Okay? Okay, so let me start off with a very strange question, which is, what is science? And for me, it's important to give you my perspective, what drew me to science. Okay? So, in my mind, science has two major components. One is phenomenology, and the other is physics. Now, some of you might think correctly, so physics is a subject, like chemistry is a subject, geology is a subject. But unfortunately, it's a bit too late. Here, physics is some sort of a philosophical view, is what so when I call physics, it's not the physics department. It's a certain philosophical view of how you view reality, okay? So just bear with me with this ambiguity. I can't help. I wish there was a separate word for physics as a subject as opposed to physics as a philosophy. Okay, so what is phenomenology? Phenomenology is expansive. It is more or less something we are all very familiar with. It has three distinct steps. It's exploration first. So imagine the simplest phenomenology is you go to a very rich rainforest, and you grew up in Las Vegas. It's an urban area, it's a desert. You haven't seen so many creatures and plants and so on. So that's what you'll do. The first step is you'll just go around exploring this jungle in Costa Rica. You'll be amazed with all the. Then after a while, you'll see there's a pattern. There are certain kinds of trees, certain kinds of creepers. There are certain kinds of things that fly. But even in the flying creatures, there are different families. So you're now doing step two. In your mind, you're started to classify. And usually by this time, the vacation may be over. But if you hung around a lot and thought about it, you'll start understanding what is the underlying systematics here. There are trees and trees, but they belong to certain families. What distinguishes one family of tree from another family? So that's the last step. So all of us do phenomenology. We're all phenomenologists in the first place. And as children, they'll understand this very clearly, all the three steps I said. But getting to the last one is not something that sort of scientists do as a matter of profession. And you might do it as a matter of just your own interests. Almost all subjects in science are actually phenomenological. Astronomy is the study of things in the sky. Botany is the study of plants. Biology is a much larger field. It's the study of all sorts of life matter. Geology is the study of all sorts of planets. And we have different planets in our own solar system. And astronomers now have planets elsewhere. We know less about them, but we know, there's so many of them. In contrast, physics, not the subject, physics as a philosophical view is inherently reductionist. Phenomenology aims to expand and incorporate all the things into patterns, and physics says, do I understand this pattern? Do I have a deeper understanding? So let me explain what that is, and I'll give a clear example. So the fundamental goal of physics is to provide what's called a physical model to explain the complex world we see, which has now been reduced into patterns, first into families and into patterns. And then inevitably, this, as best as we know, has to boil down to mathematical statements. So the only things we understand in science is when you can state that in a mathematical fashion. And that's the reason physics rose first. Later chemistry. Only now we are sort of understanding biology because the complexity increases. In some ways, physics is the simplest. Chemistry is a little more diverse. You can form all sorts of molecules, but biology is incredibly complex. So it's taken a long time. We now have a subject called theoretical biology or biology of life. But it's just in the beginning phase. Physics did this hundreds of years ago, and I'll give you an example. So you have to make mathematical statements, which inevitably, bear with me, it means, as best as I can tell you, inevitably now it means each mathematical statement corresponds to what's called a differential equation, because you need that to actually do the computations. I know this might sound a lot for a popular talk, but I assure you, you'll be so happy after listening to this. I now understand. So we now have a theory for the universe, which is not all of it, but we understand what I would say the broad geometry of the universe. We don't know why it began, but we know when it began, what parameters, 7 parameters, and I can tell you the beginning to the end of the universe. That's amazing, right? We have mathematical statements and 7 free numbers. For that, you have to make measurements. So let me give you a classic example. I've sort of given you. Let's start with stars and planets. So thousands and thousands of years ago, 10,000s of years ago maybe, humankind everywhere noticed the sun sets and you see the stars come up, and they noticed there are two kinds of objects in the sky. There are things which we now call as stars, and they bear a fixed relation. If there's 4 stars and they look like a rectangle, then the whole rectangle rises and sets. It doesn't get squished around. But there are a few bright objects that moved with respect to these fixed objects. And they were called as the wanderers because they wandered against this, what we call as a fixed sphere, and those are the planets. Okay, so we already done our observation. We have 2 families, fixed objects, moving objects. And over time, people realized that these planets show periodicities. That is, the Egyptians had already noticed, for example, the Venus, when it appears on the other side of the sun, is very strongly related. There's something they could even predict. The Mayan calendar was based on the orbital period of Venus, for example. So Brahe, in the mid of last millennium, he about 1500, I don't remember now, he undertook a lifelong study of finding how these planets move. So you measure their positions as best as you can against the stars. He convinced the king of Denmark to make a huge donation. The total project on this island of Uraniborg, which is between Denmark and Sweden, if you happen to go, was 1.7% of a year's GDP of Denmark at that time. Okay, it was one of the grandest goals. But he spent his whole life, collected all this data, and realized that someone had to analyze this. Fortunately, he had a generous heart. He gave the data to Kepler, and Kepler did the last step, which is usually the hard one in phenomenology, which is to discern the underlying pattern. So we have 3 laws of Kepler, which comes from Brahe's lifelong achievement or lifelong work of collecting very hard-won data. First, the law of ellipses. Planets move in elliptical orbits. Second, the law of equal areas. The area swept by planets is constant. And the third is the law of harmonies, which is the square of the period, orbital period of the planet, is proportional to the cube of the orbital separation. Okay? So these are now statements, but they're not yet mathematical statements. They are mathematical, but they don't have a physical model. Okay? We made a statement that looks mathematical because I can write all this as mathematical statements, but we don't have a physical model. Okay? This had to await several centuries to Newton. And not to worry, okay, there's a warning here, you'll see a differential equation. Okay, so Newton introduced differential equations. It's very simple. Velocity is the rate of change of time. We all experience this. You get in your car and you move, right? And how much you move per second or per minute is your speed. That's what x is the distance, t is time. Okay, so velocity is a very simple concept. You hit the accelerator, you move fast even within the second. Okay, so it is what's called the next derivative, if you wish. Okay, so the rate of change of position is velocity. The rate of change of velocity is acceleration. And Newton said the force, this is the start of mechanics, the force exerted on an object is proportional to the mass times the acceleration, okay? But you can express this on the right-hand side as now we're introducing calculus, okay, which is very intuitive if you think about what speed is. It really is how much you move per time, okay? dx means how much you moved in some unit, dt is how much you moved the time it took to move, okay? So to solve this, and then when he was sitting, under the apple tree, and because they had the equivalent of COVID, and he had gone home, and unlike most of us who had then, just munched away on the apple, he said, "Why did the apple fall on me?" And he realized there's gravity which pulls things down, and he proposed that the force due to gravity is proportional to the product of the object and the other object, divided by distance square, like the inverse square law. Like a candle, the intensity goes down as a square of the distance. In the same way, the force goes down as a square. It's a proposal. It's not like he had any deep reason. He said, it looks to me it's reasonable. But in order to solve, so he had all the elements here at this point, because you have the sun, you have planets. He knows how to, but he can't do it. He was not able to do because the development of calculus, how to take these statements and solve, had to wait 20 years. So Newton and Leibniz, and separately into the Kerala school, they actually had to develop calculus, okay? And it's the development of calculus that allowed Newton to actually solve, and bingo, out of the equations he was able to solve, he got all the three laws of Kepler explained. Okay, so we have one differential equation here, okay, and one thing which we don't know. I told you there's, in all these things, there's some fundamental theory which we don't understand, but you can make this measurement. It's called Newton's gravitational constant, and you have to measure that. It doesn't come out of anything. Okay, the next step, if you're really ambitious, say, can I come up with a theory which explains G, but we'll not do that today. Okay, that's way ahead, okay? Okay, so I hope you've given an idea how science proceeds. Science proceeds by us understanding data around us in a systematic fashion. No data, no science. Okay, there's this idea, oh, well, we'll sit around and by pure thought contemplate science, and which is happening a lot in modern science. There's I won't go and rant and rave, but there's a whole group of people in science who basically view the whole problem as a mathematical problem, and they're called string theorists, okay? But anyway, let's not make any bad jokes today. It's too early in the lecture, okay? So, so the role of technology and mathematics is that in order to make discoveries, collect data, you need technology, okay? So I would say that discoveries, finding new stuff, new facts, is fundamental to any science. And I love mathematics, but I have to say there's something very mysterious about this subject. It seems, as I told you, in modern science, if you can't express your understanding in a mathematical statement, you haven't understood it at all, okay? That bothers me a lot. It's this one thing, it's a question I always ask myself. If there's another civilization, will they have also the mathematics like we have? Because it seems invariant. You can have different languages, you can have different music, that's fine, but 1, 2, 3, 4 apples, no matter which symbol I use, it's still 1, 2, 3, 4 apples to you or to anyone. So it's hard for me to understand if I go to Klingons, will they be having a different mathematics? I don't know. So there's an idea that mathematics is a true universal language. Okay, but again, it's this bit beyond the thing, but I'm puzzled by that actually. Well, this is not enough because mathematics can only take you so far. Then you need computational technology to actually solve these equations. Only the simplest equations can be solved in a sort of a simple, what is called analytical solutions, which require only a modest calculator to compute. But most problems really require large computers because these differential equations get very unwieldy. Okay, I've given you my big, long introduction of science, and then we'll plunge into the story of the periodic table, which is the main talk, and then why this story gets us into what I actually ended up doing. Okay, so as all of you know, the universe was born, about 13.4 billion years ago. I can tell you that on safe grounds, this is true. Okay. When it was born, it was very hot. It was so hot that all matter that we understand, would be gaseous, or it was called a plasma. Okay. But if you looked at what is inside that plasma at the birth of the universe, close to it, we had to wait a few seconds when very hot stuff like quarks and all disappeared, and they start forming ordinary things like nuclei, electrons, and protons, and so on. Okay. So after the Big Bang, there's a very short microsecond, there's all sort of nuclear physics which we'll ignore. But very quickly, just a few, let's start with a few microseconds later. Okay, we'll simplify our life a lot. Okay, then we now have protons. But if you wait 10 seconds, now we start getting things we understand. For example, at this point, we have hydrogen and helium. That's it. So if you go to this periodic table, 13.4 billion years plus 10 microseconds later, this periodic table is hydrogen, helium. That's it. Okay, so, but you should now be wondering what's happening here. You know, some of you may be thinking, you know, maybe you don't like a colleague, you say, oh, what a helium bag he is or something. But really, we don't have any helium in us. We have some hydrogen, but we have a lot of other things. So here it is. The universe has hydrogen and helium, but we and the Earth's crust, which we are part of in some sense, has everything else. Hydrogen. How did we go from this hydrogen-helium chemistry to this one? Okay, that is the gist of what the project we have undertaken, not just us, but this whole field, okay? So I would call this, how did the periodic table come about? You know, and the dean here is a chemist, and, you know, so he has to be very happy. Thanks to the astronomers, chemistry began, okay? He would have been without a job otherwise, right? So we are going to tell how chemists got their jobs. It took a while, and that's the story I'll now tell you. Okay, the story involves stars, their life, and their death. Stars, during their life, like the sun, if you look in the sun, it's converting hydrogen into helium. It's called fusion. And if you wait long enough, another 5 billion years, it'll take that whatever is helium in the center and fuse it to carbon and oxygen, and then it dies. But it's more massive, it dies more spectacularly, what's called a supernova. And they give rise to bumps and burps in the night sky. And that's where you start getting other elements, all the way like silicon, magnesium, calcium, and in particular iron. Okay? So, what's a supernova? Supernova phenomena is straightforward. Here's a nearby galaxy, very popular with amateur astronomers. And you take pictures of it every night. And then you find one night when you take a picture, there's a new object. Okay, there it is. There's this new object. It's not there. If you just do a blinking between these two, there's a new one. That's a supernova. And in this galaxy called Messier 51, otherwise known as the Pinwheel Galaxy. It is in this supernova that the higher, what I call Z here refers to, as I go down the periodic table, the Z is changing. Hydrogen is 1, helium is 2. You go to iron, it's 26, and so on and so forth, okay? By the time you reach 100, you're more or less end of the periodic table. That's called the nuclear charge. So the higher Z elements start getting built up in this very explosive phenomena. So the systematic study, this required a systematic study of the night sky, and this began with Professor Fritz Zwicky, who was the first astrophysicist employed by Caltech when they began the 200-inch project. And he had this idea that it's not that people didn't know variable stars, that stars flickered, but he said, I want to take a very systematic study so that you can say this is the rate at which new objects are coming and so on. So he employed a then new invention called the Schmidt camera telescope to undertake systematic study of the large field of imaging of the night sky. Okay. So this is, it's a technical term, but it's very easy to explain. It's called a phase space. So you find these things that explode, they come up, and then they reach a certain brilliance, and then they decay. So we have two numbers. What is the peak brightness, and how long did they live? So this is how long did they live, meaning how long were they visible to me, 1 day, 10 days, 100 days, a year. And this is how bright they are. Forget the units, and it's a log unit, both are log in this scale. It's a wide range here. And he found that he and his colleagues, they found two kinds of explosions. One they call novae, which is nova stella, new star. and they're found in our own galaxy. And the other, they call it supernova. When they introduced that term, it was a new term, so it was super-nova. Nova was known, so supernova. But now it's entered our lexicon. We no longer hyphenate it. It's a regular word. Okay? And you can see there's like 10,000 difference in their brilliance. Okay? So it is these supernovae that, here's a summary of what astronomers have learned starting the last century to now. You can take the periodic table and recast it in a different manner. It tells you who came from where. Okay, so let's do something like calcium in your teeth. It's green and blue. Okay, there's green, exploding massive stars, and exploding white dwarfs. So please thank these supernova 1A and massive stars for the calcium in your teeth. And how about iron? Iron has a bit more of the exploding white dwarfs. So the iron in your blood came from these white dwarfs, which are dead stars dying again. It's pretty bad, right? This star had to die twice, so you got some iron in your blood. Okay, how about gold? I'm sure all of you want to know is gold, silver, platinum. Okay, there it comes out, these are neutron stars, which are another kind of dead stars, and they have to die again. Okay, so you get your little bit of gold, silver, platinum. Okay, so this project I began to sort of following Zwicky maybe 100 years later was to do an industrial exploration of the night sky. Okay, so you'll get to hear the engineering side of that as well. So I have to give a little bit of a background of my own style. I finished my PhD and been at Caltech. This fall I'll be there for 40 years. It's the longest home for me. It's a wonderful institution. It's more or less meant for research, and I can tolerate people like me. I may appear charming now, but some colleagues would disagree. Like in today's meeting, they already, I think, ruffled some feathers. Okay, so, but every 5 years, 10 years, I switch subjects. I just like the idea of there's only one life and I want to experience different things. Okay, so I was working on a field called gamma ray bursts. It's something that Professor Bing Zhang here has focused a lot. And I worked for about 8 years, wrote lots of papers, and then, this was in 2004, November. This is a launch of an observatory called Swift Observatory, okay? And I'd gone to the Cape, and on the way back, flying back, with this gamma ray burst used to be a sort of a field where there was only one gamma ray burst that was being found for a period of 5 years, one a month, and this was the first time they could localize. So this was the pioneering days. It's sort of, like when the West was discovered, not far from LA is Placerita Canyon. Many of you probably would not know this. If I ask you, where was the first gold strike in California? Any answer? Wrong. Sutter Mill, wrong. Okay, it was in Placerita. It's only, you just go up on the way to here, actually. On the way to Palmdale, Placerita Canyon. It was found about 10 years before in Northern California. This guy, Shepard, was walking around and he stumbled, and it was very heavy, and then, wow, that was gold. So when things are new, you don't have to be all that bright. You just have to be there. Okay, and that's exactly what I've done. It's like, forget being bright, that's hard. Just be where things are happening. Of course, that's the part that sometimes you have to work hard to arrange. Anyway, so I said, okay, the GRB game was fun, wrote all these early papers, and this mission was going to do a GRB every 3 days. Now, that means everyone and their brother and their dog will be working on this field. Time to bail out. Okay, so anyway, so that's what led me, and I said, okay, I was looking at this, teaching a class. I said, okay, we have this novae and supernovae. Is there some stuff in between? Okay, now there are two kinds of people. We'll do a psychological test. Okay, all of you look at this figure carefully. Okay, contemplate. Okay, there's a group which I'll call as physicists. What they see here is they say, there are two families with some underlying parameter, which is this family and that family. you're a good physicist because you're reducing the image into two succinct statements. Some other people may say, my God, there's so much white space here. You're an astronomer. You want to go and find stuff there. Okay. So, physicists are smart people, but they kind of lack imagination, I think is what I was trying to say. Okay, so, and it turned out that I said, okay, if there are these objects, I started looking around, and I won't go in detail, but I made this, and I noticed in the chit-chat that was going, there's a new object in another Messier galaxy, and that didn't look as bright as a supernova, not as faint as a nova, and right away I wrote a paper to Nature, which in our game is like marbles. When I was a young boy, they're ordinary marbles, and they're marbles with patterns, and they're extra 10 points. If you publish in Nature, it's like that special marble. You got extra 10 points. Okay? Anyway, so publish a paper in Nature. I knew right away that this is like the Placida Canyon. Think about it. Next thing, you're stumbling around discoveries. Okay, so I said, okay, now we have to move on to the next phase. Concept is good. And by nature, I'm an engineer. Okay? I really like to build powerful instruments, literally with this idea that you build highly sensitive things and stuff will happen because the universe is so rich. There's no point for me to try to use my feeble imagination and make up stories. Just build a powerful instrument and you'll find things. So I was talking to a friend of mine as a professor at Santa Barbara, and I said, I have this idea. I want to do industrial scale astronomy. And then he said, well, I'll introduce you to, why don't you come this weekend? So I drove to Santa Barbara, and I had a lunch with someone he had set up, and the Santa Barbara Wharf, right there. Lunch started at 12, supposed to end at 1. It finally ended at 5 p.m. And this gentleman called me the next day and says, Shri, I really like your ideas. In what way can I help you? His name is Wayne Rosing, and he was the vice president for research in Data General, Sunwork Systems, and Google before he retired. Okay, obviously a man of what you call high net worth. And I said, okay, Wayne, give me $1.5 million and a 6-month option period. Now, that's not something most scientists do. They want, give me $1 million, and they want, the reason is it's extremely important for me. If I want to get things done, you have to get it done as though every day counts. So I said, in that time, I will double the money by actually getting other people to buy into this idea. I could ask him for $3 million right away because he was very impressed. But no, this put me on a directly bold thing where if I can't convince other people to put the money, it's a validation of my idea. So, and 6 months is just to get me done. If it doesn't happen, yeah, let's move on to the next thing. Okay, so I'm always impressed. There's some scientists who can spend 30 years of their life. And I was like, wow, how do you guys get up in the morning and go to work? Because for me, if things don't happen in 3 years, I'm done. Life is too short for such things. Anyway, 6 months later, I went around the world, collected money from various universities, and we launched this project called the Palomar Transient Factory. Here's an aerial view. The novelty then was we used multiple telescopes. People had, as a system, which sounds obvious, but in 2007, it was not so obvious. Being the director of the observatory helped. I could take the decisions very rapidly. Okay. So we used these two telescopes, 100% for this project, and this to do some. And the other thing is I always very carefully choose who I work with or which students. And I found this bright young woman. And I have a simple rule. The brighter they are, the higher the risk project I'll give them. The reason is if they fail, they can recover. If you're not so bright, you can't recover well. So I told Mansi, yeah, you're fine. If it doesn't work, write some simple papers and get a PhD. Anyway, so a lot of young people, I had them right out of grad school. Nick Lloyd finishes PhD in Cambridge. He got project scientist. That's a very big job. He's really in charge of all the hardware systems. Quimby from Texas, he was given software lead, possibly the worst job because people write bad software and his job was to integrate all that. Anyway, so in 26 months from discussion with Rosing, we are on air. And all we do is very simple. Take a picture what you call the reference image is an old picture taken, a month ago, compared to the new one. We do what's called subtraction. Here's a new one. Well, that's supernova, but not all the time it works that way. This is subtraction. Then you say, this looks a bit more fuzzy. And here, what about this guy? Then no, this is systematics. You can't have two supernovae so next to each other. It sounds very improbable. So there's a lot of machine learning. And fortunately for us, the human eye can recognize this. But fortunately for us, machine learning came in just the right time. So in 2009, we began. And one of the first things that really helped us, because or took the human tedium out of this, was machine learning to distinguish false from true. And they're all different, various thesis projects. The students who worked on this, they must have fun of their life because they're really there at the forefront, okay? And usually when I start a project, I only want to have a 3 or 4 year thing. And this is another mistake most people make. They think it's like projects are like investment. Like Warren Buffett, you buy and hold for a long time. But that's not what it is. This is something else. Whenever you start a project, you should have an absolute sunset clause understood, put in, because that will make you realize every night counts. So I said, we'll do a 1,000-night survey. It's like 3 years. Then every night counts. And then it gets you going. If you don't put a sunset clause, you just become lazy. And then you just end up doing the same thing again and again. So there's some people who worked on the same topic for their entire life, which I could never, ever understand. At that point, I'll have to say, come shoot me now, or whatever equivalent, Anyway, so it became so successful that we started another project. But we realized we need what's called spectroscopy, which is studying, we find the object, and then we need to use a prism to get a little rainbow, like you've seen in textbooks. And the details of that rainbow tell us what elements are in there. Is there calcium, is there iron, and so on. So we invented a sort of a new style spectrograph, which could do all this robotically, and otherwise it's largely done by humans. Okay, so I had to tell you a joke which annoyed my colleagues. I said, the best way to do astronomy is to get the astronomers out of the dome. Okay, and they thought I was talking about them. Well, it's true. Okay. Anyway, so all this stuff, then there's a needle in a haystack search. That is another PhD. That's how to do large analysis in the same night. You get a large amount of data. So you need, at this point, artificial intelligence and machine learning. So what is the thing we have? That stuff started with that novae and supernovae. Now there's stuff over here. The astronomer is winning over the physicist. See, there's white spaces slowly getting filled up. Okay? Okay, so I was so surprised the second phase worked with the automated spectroscopy. I said, okay, why don't we do the next big thing? The US government had sanctioned a major project. It's about to be completed now. But I'm talking years ago, called the Large Sign Optics Survey Telescope. It's now called the Rubin Observatory. It's a $1 billion project. And I said, well, we could do maybe a tenth of that right away by taking ours and building a new detector system. So that led to a much larger project. So we started with that 1.5 million times 2, 3 million. Well, now it's a factor of 10 jump. This is a 30 million project, has people all over the world, all the agencies. So we built a very large camera. This camera is 47 square degrees on a small telescope. The smaller cameras on large telescopes, they have other advantages. But if you want to go find the bright stuff, we win. Now I'll go through these slides very quickly, but I just want to give you a sense. A lot of astronomy is not what you think. Some of you think, oh, these astronomers are so romantic. They go in the middle of the night. They can see the starry sky. No, that's not what we do at all. This is a huge engineering project. This is the engineering team. And I'll just flash through this. We had to redo the whole telescope, build one of the world's largest cameras. Okay. And I'll just give a sense. This is one of the world's largest cameras. It'll soon be displaced when LSST comes up. Here, a mosaic of CCDs. These are exquisite images, like in your cell phone, but that uses what's called CMOS technology. They use silicon technology, and these are perfect detectors. The surprising thing is the cell phone stuff are getting really quite good. Okay. Okay, so we have to do various subsystems, upgrades, other upgrades. Finally, here it is. installed. And we needed one part, and the contractor, a small company in Pennsylvania, they decided to delay that part. And then it's called, then they're in what's called a crisis for us, because we have all these people who are paying, and now all of a sudden for 6 months we don't have this part. It's the thing you never want to get caught on. And our friends in China helped us. They produced this aspheric optic, this institute, in record time. And we had set aside $300,000. They said, that's what we'll give you. They said, no, we only want $50,000 because that's the money we spent on material. I said, what about labor costs? They said, instead, if you can take one of our students every summer for undergrads. I said, yeah, because I did a calculation. Each of them is 5K times 2, 10K, 10K times 5 years, 50K. 50 plus 50, 100. 100 less than 300. End of story. Okay. And of course, they knew because they in fact have a number of very excellent Chinese students have gone through this program working with me. I did tell them one thing: please don't send me bad students because I can't, I have some limitations. So they used to have a competition to select good students in China, and they're really very good. We achieved what's called first light, looking at Orion. This is the size of a camera, and that's the Orion Nebula. I don't know if you can dim the lights, it would be nice. That's a big trapezium. Okay, and this is a huge software project. We had a professional data center, archive center, IPAC, located campus. And the Heising Science Foundation, we are very lucky because this was so exhausting because we're going at high speed, and they gave us $1 million to do the science. Otherwise, I wouldn't have been able to do science. We start with this. We use many facilities around the world, and in space, on ground, radio, optical, X-ray. And here's, okay, this I was planning to update, but I forgot to update. Okay, this tells you, this is like how many McDonald's hamburgers have we served kind of advertisement. Date, number of supernovae that we classified, not that we just found. Okay, to give you an idea, before we started, there were only a couple of hundred supernovae being done in a whole year by the whole world. And now we can do 10 a night, and in a year, like a couple thousand, and we now reach 10,000. I said, that's enough hamburgers served, we're done. We should do something else. And you may say, why is there stuff missing here? That's in the south. We can't dig a hole through ground. There's some stuff missing here along the equator because that's the Milky Way. There's a lot of obscuration, so we can't see through that, okay? Okay, with this large discovery rate, you always find some very interesting things. So if with these thousands and thousands of supernovae, occasionally there's a simple chance. Imagine I'm the supernova, you're the observer there, and right in between us is an intervening galaxy. So the light rays would go here, but they get attracted by this galaxy, so they bend before reaching you. And that produces an Einstein ring. That's called a gravitational lens. It's a real ring. And then it splits the stuff. We had Hubble observations. With this one image and some data, you can actually deduce the geometry of the universe. If you have about 6 of them, we could do just as well as any other technique. Okay, but for this to happen, it turns out we had to do a few thousand to get this. Okay, so I hope you're now getting slowly convinced. Do increase your capacity to discover, and ye shall find. Okay, sometimes by pure dumb luck. That's fine, I'll take it. Okay, now we have a solar system. The sun will age in 5 billion years. It'll get large, it becomes what's called a red giant. As it ages, becomes large, the planets will start getting engulfed by the sun, and they'll be destroyed, but it's 5 billion years. I don't think you should really be traumatized. We have other problems right now, I think. So we have seen this planetary destruction in action, okay? And so I told you get 10 points if you publish in Nature. Well, you get 20 if they put you on the cover of magazine. Okay, so here is planetary destruction. This is a PhD student who finishes now at Columbia as a faculty member. This is a cartoon artist's conception of what's happening. We actually see when the planet gets engulfed, we see light go up, we interpret this and so on. Okay, so this has been a very good project. And I'll start winding up now. let's revisit that old diagram. I started off with the novae and supernovae and Zwicky and so on. Then I showed you at the end, before ZTF, how we are already seeing that nature is rich and astronomers are right, physicists are wrong. No, okay. And now let's look at this diagram with Zwicky now. You won't even recognize at this point, because here this only goes from 1 day to 1 year, and in these units from -6 to -24. Remember that? Okay, now it's going from 10 to the -3, which is like some tens of minutes, okay, to a year. That used to be some minus maybe, but that's not -35, 10 magnitudes more. It's very much brighter. So there's stuff all over, okay? And so, well, but maybe this is the other part I should boast about. You know, we 12 PhD students, 12 postdoctoral fellows, and in 6 years we are publishing a paper every 10 days. Shows you don't have to be that bright. If you have the right equipment, the papers get written, okay? And we put out the data and the alerts in real time. The rest of the world can consume it too. And every paper we publish, the rest of the world has to publish 4 more. So we're huge, what I call a halo factor. It's called branding. You shine by yourself, and you shine because people shine light on you, okay? And we helped our alums. So one went and started a company called Wise.io. Then he sold it to GE using machine learning proven on our. And another one has formed a company for software automation. And a couple of them went to startups, Weights and Biases, and Google, and also Google. In fact, the main reason they do is they finished their PhD, and this student Yisa, who was very bright, he got a fellowship at the University of Washington, which is a very good place. They have a nice big data fellowship. This years ago, maybe 10 years ago now. At that time, it was like $65,000. But you know, as a fellow, you can do whatever, mingle with astronomers, with data scientists, computer scientists. And then a few months later, Google offered him a job. Then he called me up and said, "Shri, what should I do?" I said, "You should ask your wife," because they were offering him ×3. They're offering him about 180,000, and he has 65. I said, "Wow, that's not a science decision; it's a wife decision at this point." Anyway, okay, and I told these people when they, you know, I'm hoping these people who made in the startup world, they will remember where they got their beginnings, and when they go IPO, they should send me 10% for research. Okay, so. Let me now wrap up. I want to have some time for questions. So I was slightly, let's say, this is a thing many of us discuss, you know, with machines doing this, what is our role and so on. I'm fearless. My view is that the only constant in life is change. This is not an original statement, I can tell you that. So you should welcome change. If not, change will crush you, okay? So my view is no, I'm going to use every technology. What is it I'm interested in? I'm interested in how the universe works. Okay, I have machine learning. I didn't have that before. And when I started as a grad student, you actually had to drive to the telescope. And then the very first one as a grad student, you actually move the telescope by hand for the big moves. And the small ones, you had a little thing, you know, we do this vernier movement and so on. We don't do that now. It's not like I'm missing that. And is it like very important to do that? So this idea that you have to be there observing and doing things, no, this is not so necessary, okay? That's what change is. So my goal is I want to, and I'm not doing that because I have not switched subjects again, but the goal I had in mind when I started the Zwicky Transient Facility was the automated discovery of the universe. Can I build a machine that will automatically discover the universe? So here's my vision. Build this big machine. It's all run robotically, self-sequencing programs, real-time, robust data pipelines, artificial intelligence, which does all the analysis, rank order the stuff. So I come in the morning, and I say, "Computer, tell me all the fun things that happened last night." And it has given me a long list. 1 million things happened, but most of them are not so interesting. Here are the top 3 things, or 10 things. I look at that, and I choose one, and I write a paper, and then I go home. Okay? And that's what I want. And the next phase I want is phase one. Phase two is I come to the office in the morning, have a cup of coffee, and there's a paper written for me already. Okay, where are we on this score? I'm happy to tell you we made some progress. A couple of years ago, our team, there's some now young people. This is a group of ZTF, which is at Northwestern. Here it is. It's a little bit hard to understand. This is how astronomers, okay, it's like our SMS or, things we communicate through something called the transient name server. It says we present the classification of this supernova, but otherwise known as ZTF 23ABHVJI, because there's so many as we find. We start with A, and then becomes AA, and then AAA, and that sort of stuff. Okay, this is a type 1 supernova. To the best of our knowledge, this is the first transient which required no human action from its discovery, meaning from the fine photons landed on the detector, to its spectroscopic classification being posted to TNS, being announced to the world. Okay, so I think this is probably a good time to start winding up. And this is my backyard in Pasadena. Fortunately, my backyard overlooks Mount Wilson, where the famous 100-inch and 60-inch telescope are located. I have a nice pool, several orange trees. The part I enjoyed the most is you can go and pluck the low-hanging fruits. I'm going to leave the higher-hanging fruits to more able colleagues. Thank you.
From your data, does it give you a good distribution of the elemental composition of the universe? And is the Earth a good representation of that, or is it an outlier in terms of the elemental composition?
Yeah, okay. The question was, is the Earth's composition sort of what you call cosmic? Not really. The inner planets, Mars, Mercury, Earth, we are the terrestrial planets. For example, where we have very little hydrogen and helium, which are the dominant elements. So with the condensates left over. Okay, the closest would be Jupiter. Okay, Jupiter. It may have a bit more deuterium than in the universe, but it would have, Sun and deuterium would be close to what you might call as the cosmic composition. So the exact differences I can't immediately tell you. It's not something I have studied, but the biggest thing missing on Earth is hydrogen and helium in a very big way. The planets which are closer to the Sun, the hydrogen and helium escape easily because they're very light elements. And so what astronomers call, I know that our dean here would have a heart attack, but they call anything other than hydrogen and helium, below hydrogen and helium, everything else is called metals. Okay, so we are a metal residue as opposed to a genuine cosmic composition. Yeah.
Similar question, in all the spectrum analysis of all of these supernovae, what would you consider the major surprises that we've seen?
So our goal right now, first I'll give you the more sort of the broader idea. Let me think a bit of the major surprises. The goal of this project and others, we are a part of a much, there's a worldwide effort on supernovae and stars going on for a long time. We've managed to do a bit of that in a more industrial way. The basic thing is, we know what is the composition of this. For every 9 hydrogen atoms when the universe began, there's 1 helium atom. We know that very well. We want to explain, on the other hand, the cosmic composition, where we use Sun as the way to measure. Why is, so for example, in cosmic composition, oxygen is 500 parts per million compared to hydrogen. Carbon is 330 parts per million. Nitrogen is 100 parts per million. Iron is maybe 50 parts per million. Okay, we want to explain. Want to have a complete model which says, not we can explain the periodic table. We can explain the abundances in the periodic table. Are we there yet? Probably not. Okay. We have a rough understanding, yes. Okay, we have a rough understanding. I would say for what are called the lighter elements, I think we more or less have a good understanding. As you go down the periodic table, it becomes a little harder, okay? Because there are multiple sources and they're more exotic sources that require things like gravitational wave astronomy, because those events are not particularly well represented in the optical sky. Okay. But otherwise, I would say, yeah, we have a reasonable first order understanding of the actual abundances of the universe as a result of star life and death. So a young candidate, yes.
Two questions. So you were looking for stuff between supernovae, but what kind of stuff is there?
I'm looking for stuff between supernovae and only in a figurative sense. That's the phase diagram, which is we're looking for objects which are not as bright as supernovae and not as dim as novae. Okay? And it turns out there are a whole bunch, so I can go back and show you a few things. I mean, let me use the simpler diagram because the new one was too complicated. Okay, so these objects, the first one I found when I had this idea that I said I got this major paper, it turns out this object, it's red, it's brighter than a nova because you go up, it's bright. The color is what it looks to you if you could see it through a telescope. So it's definitely brighter than a nova, but dimmer than a supernova, and it's red. We now believe this is, many stars, unlike the sun, actually are binaries. They have a companion. If the companion is close enough, as the star expands, so the sun as they get older, it expands, they engulf. Like you have planets getting engulfed, one star engulfs the other star. It's called a stellar merger. So these are all stellar mergers. Then we have some things which produce a lot of calcium. This is a little unclear, okay? So someone asked, okay, do we understand all the sources of calcium? I don't know. There's this group here, and we believe they come from two white dwarfs having a very unusual channel. So maybe the calcium in your teeth come from these very weird explosions. They're not common. So each one of these is like a story in itself. And right now we're putting this in one group. This one we sort of understand, but not really well. This one, we know what it is, but theories are not that clear. Okay. So it's so that's where we are. Yes?
These all came from hydrogen and helium originally.
Yeah.
What was there before hydrogen and helium?
Oh, what is that before the Big Bang? No, you're not getting me there. Then if I answer that, you'll say, what about other universes? No. I'm a very practical guy. You should ask some string theorists. I can tell you. I recommend, okay.
So have you been able to correlate some of these events to physical parameters like pressures and temperatures, or why these different phenomena produce different elements?
So the correlation is usually done to the location. Like in real estate, location is everything. There are two types of galaxies. The galaxies that massive, the pinwheel galaxy, is making stars as we speak today, and the dead galaxies. They tend to be red and dead, and they're called elliptical galaxies. So some supernovae happen only in elliptical, okay, not in spiral. So we are able to correlate their progenitors. That's our big focus, okay. And for some of these explosions, we can actually do some sort of CSI-like thing. We can undergo some sort of a postmortem, because as the supernova explodes and gas moves, it will actually go through what the progenitor had shed mass, and we can actually see the composition in that thing. So that's called mapping the supernova type, or the supernova itself, to its progenitor. And that's a major focus of what we're doing. And we have again, there's some surprises compared to the old theory. The old theory assumed stars didn't do much. They just sat in the did fusion and then one day exploded. It turns out they're a bit more complicated, which shouldn't surprise us. That as the star ages, it starts losing matter already. And sometimes the star knows it's going to die, which I don't know how that happens, because it's death omens, and puffs up a bit more. So there's all these additional complications, which is what we are finding. But the story in its first order is fine, you know. Yeah.
So how does dark matter fit in?
Not affected by this at all. Dark matter, where, you know, it is hard to study this because it doesn't interact with ordinary matter. Okay. Which means it won't participate much on in the star business. Dark matter basically provides a lot of gravity, but not much action. Yeah.
Do you have anything you might add to the current destruction of Betelgeuse? Or maybe it's not.
I don't know. Yeah, no, I've not been following it up, you know, but these stars have to explode. No, as an astronomer, I'd like a nearby star to explode, but maybe as a citizen of this planet, maybe a little less so. Yeah, because they can be pretty disruptive. So I will tell you this one thing. There is very special, some small number of stars, fractional stars, I mean, massive stars, they die through gamma ray bursts. Okay, we have ideas what they could be, but let's not go into that. But they die in a very spectacular fashion. And they put out, when they die, there's a supernova that explodes, and amazingly enough, we believe there's a new black hole accreting matter. You get jets of very fast moving material. And if you are on that axis, you'd see very bright gamma rays. Now, most of these gamma ray bursts we've seen are in other galaxies, very far away. Okay, however, if there's a gamma ray burst in our own galaxy, and this jet is directed towards us, gamma ray is very good at dissociating molecules. Okay? So it will dissociate molecular nitrogen, molecular oxygen. It will form nitrous oxide, and we'll all end up dying but laughing at the same time. I think that's, the best way to go.
Yeah, quick question. Is the type 1A supernova are used as a measuring standard?
Yeah.
Are they a single dot on that plot? And maybe you
No,
have, like,
they are that little arc. So that
filling in
was
the white, since you're filling in the white part, you have like a type 1A dash 1.
Oh, yeah, there are a whole bunch. There's a type 1AX, there's a type 2002 ES, 9190. They're all outliers. And we know this because there's an astronomer who really deserves, in my opinion, the Nobel Prize for that is these 1A supernovae, they're not like standard candles in the sense each ruler is exactly the same. The rulers are different sizes, but they follow a pattern. The brighter they are, the longer they live. Okay, and he figured this out, Mark Phillips. If you apply that correction, then they squish into a pattern. And the things which are outliers, which are at least half a dozen families, because it turns out in an optical sky, 2/3 of the supernovae we see are those actually. So this picture doesn't give the density. Okay, so if you really want to understand what their density is, you should observe this other movie closely because it actually is telling you who's doing what. Okay, somewhere here, yeah, see? Exploding white dwarfs.
I'm going to show you why you need a DM. Okay?
Okay.
You go and you press little buttons on the wall.
Wow. Well, it's good to know deans can do some useful things. So this one's happening. Exploding white dwarfs, those are the 1As. Collapsing massive stars, supernovae. So you can see the red ones are the most common ones. They're about 2/3 of this.
Maybe let's take one more question and the rest of you come down and talk to the speaker. So yeah, who wants to ask one last question?
Yeah, go ahead.
So, sir, based on the elemental composition of Earth and, as you said, Jupiter and everything else, we're clearly in the area of remnants of a supernova, multiple. Do you think that's common among other star systems, or are there other exoplanets that are just carbon and just have hydrogen, helium, and the rest of the star system?
Yeah, Well, the Earth's the one thing we know, the solar system is something we understand very clearly. We are clearly rocky planets, and then gas giants like Jupiter and Saturn, and then icy planets like Neptune and Uranus. Whereas in other solar systems, they have what are called super sub-Neptunes and so on. And there's a lot of debate whether there'll be, would they have oceans and so on. You know, I'm not really an expert on that. But it'll be very hard to just make a purely carbon planet. Unless it's some very special case. So around these millisecond pulsars, you can actually get a purely, basically it's like a white dwarf, a very small white dwarf. It'll be a purely carbon oxygen planet. And I will tell you a fun story about that. The first thing after my thesis, or just when I was finishing my thesis, by sheer accident or otherwise, I discovered the first millisecond pulsar. So I was interested in this for about 10, 15 years. And these pulsars they are born in binary systems. It's a neutron star, companion grows, feeds matter, spins up, that's all it millisecond pulsar. And then the pulsar, the evil pulsar, has a beam and it starts frying the companion, which spun it up. And that's what I call black widow pulsars. Okay, and the stuff it leaves then is this carbon oxygen core. And so, you know, as usual, you know, it's some observations, got some data from Tech, bashed through a Nature paper. And in this, you have to always understand advertising is very important in this business. So we had, this is the universe's largest diamond, and we gave the number of carats. Okay.
All right.